All right, so if we are actually working with a double integral where we recognize that either the function or the region is going to be simplified by switching to polar coordinates, then what we're going to do is we're going to do that switch to polar coordinates and see how it happens in our integral. So notice that this double integral might just be doing a double integral, or it might be finding an area, or it might be finding a volume. So we can keep those in mind as well. But in general, we would have that our xy coordinates, well, x is congruent to our cosine theta, so the x's will become that, and y's are congruent to our sine theta, so we're going to do those substitutions for x and y in the function. And then instead of defining my region using x's and y's, we're just going to try and define the region using r's and thetas, where I am going to add the restriction that I want r to be between two functions of theta, and we're going to have both of them be positive. So you can always choose to look at positive r values. So we'll have r is between g1 and g2, so two functions of theta, and then theta is going to be between an angle alpha and beta, where I do want a restriction on alpha and beta so that the difference of alpha and beta is between 0 and 2 pi. In that instance, what we're going to end up with is we're basically just going to convert our things over. So when I convert the region over, what we're going to end up with is instead now we're going to do like a dr d theta, where dr is going to go g1 of theta to g2 of theta, and then theta goes from alpha to beta. We're going to sub in the x's and y's, so this will be f of r cosine theta, comma r sine theta. But it turns out that this isn't going to be an exact equality as is. What we need is we need this extra scaled factor that's going to make the change of coordinates appropriate and work in essentially make it work. And we're going to explain this more in depth later in the class, but what we end up needing is an extra factor of r in here. So we're going to take the function and we're going to multiply it by r. So kind of a simple, silly thing that people do when they try and remember converting to polar coordinates is we always need an r dr d theta. So it's kind of, you say it like a pirate. So an r dr d theta. So that r is the special scaling factor that allows the change of variables to give an accurate equality for the two integrals. One of the ways to a little bit convince us that that r is necessary, so it is always necessary, r is always needed, even if we switch to, like if we choose to do d theta dr as our order of integration instead of dr d theta, right? Like if you think about it, we didn't do it in the other one, but when you do have both of your bounds being numeric, with x's and y's, that just represents a rectangular region. So it doesn't matter if I look at x's and y's in either order. You end up with the same region. The same is true if both r and theta are numeric. So like if you look at our examples from the last video, right, if I instead look at theta goes from 0 to 2 pi, and then r goes from 0 to 5, I still end up with a circle of radius 5. Because basically it's just, okay, first we're thinking about swinging theta all the way around, which gave me the whole plane, and then I scaled that into just looking at certain r values. So it still scales it down. So you can do that if you want, but no matter what, that r has to be multiplied by the function. And one of the ways to see why this is true is to think about, recall, if my function, if f of xy is 1, then this integral gives that area, right? It gives the area of R. So that should be true here as well. So we can see here, if I do the integral from alpha to beta, the integral from G1 theta to G2 of theta of 1 times R dr d theta. Notice if I plug in x's and y's, it still just stays 1 in the integrand. That doesn't get affected. So then we would be integrating R dr, which is going to be the integral from alpha to beta of R squared over 2. That would be evaluated from G1 of theta to G2 of theta, and we're going to do this d theta, and take a look at what that simplifies to. We have the integral from alpha to beta. If I plug in G2, we're going to square it, so I'll have G2 of theta squared. There's a 1/2, let's pull it out front, because there's also a 1/2 in the second one, so then I subtract off G1 of theta squared, and all of this is taken d theta. And this is exactly the area formula that we just recalled in the last video, because notice what we're doing 1/2 r, the outer radius squared minus the inner radius squared, integrated with respect to theta. So it does convert back to a area formula that is a polar area formula. It kind of makes sense that the two would have to be different, that we would need something like an R in there, because like when we did area under a curve with rectangular coordinates, all we had to do is integrate the function. When we do area under a curve for a polar curve, we need 1/2 times the function of R squared, because they use different area formulas. They're based in different things. One of them is doing length times width. One of them is doing 1/2 angle times radius. So we need to have some sort of conversion there to make them make sense and coordinate together. It's not simply that the coordinates need to convert over. We also need to adjust the area formulas to convert over. So this does work. This would give me the area of the region, which is good. And so then again, when we're doing something like volume, when that function on the inside is not just a 1, this still then would just be that idea of area of the base times the height would give the full volume of the surface, or the volume under the surface. What we're going to do for the rest of this section is a bunch of examples. So I'm going to take a look at most of those examples, working them out through a screencast rather than at the board. So it'll look a little bit different in a video, but you'll still have a sequence of videos to watch to finish up this section.